For this next section, we're going to explore the limit of a function, both the intuitive definition of a limit and all the varieties of limits we can look at, as well as some computational methods. So to start with, just up here on the screen, I have what we call our intuitive definition of a limit and our actual limit notation. So let's suppose that we have a function defined for all x near a point A, near a point x equals A, except possibly right at x equals A. So we'll get into that piece, this statement right here, except possibly at x equals A, when we start looking at some examples. So if f of x gets arbitrarily close to some value L as x approaches the value A, then what we say mathematically is the limit of f of x as x approaches A is equal to L. And so here is the notation. And if you need to freeze the screen here, pause the screen, copy this down in your notes, please do. The limit of the function f of x as x approaches A. And when we say mathematically x approaches A, that actually means x gets infinitely close, like so close that x and A have an infinitely small amount of space, you know, if you want to think of a visual space between them. Okay? And so the limit of the function as that's occurring is actually equal to L. Okay, and I just caught a mistake. It could be equal to A, that's true, but we don't necessarily want to guarantee that it's going to be the same value. So I just caught a mistake on my screen, and so please do fix that. That should have an L right there. So the limit of f of x as x is approaching A is equal to L here. It's equal to L. Okay, so we're going to talk a little more about what I had down there at the bottom of the screen, just some ways to compute limits, but I wanted to give you a visual for this intuitive definition of the limit. So let's just come over here and let's make up a function. So we have a graph here, and let's just suppose that our function does something like this. If it comes up and hits that point right there, and then and also comes up, and it looks something like that. So let's call this y equals f of x. So if we take this function and we consider a couple of limits, so let's look at a few. So for instance, what if I wanted to find the limit as x approaches 0 of this function of f of x? So what we're looking for here is we are literally looking at zooming in. Here is 0. Actually, I didn't write 0, but this is obviously 0. This is the origin right here where the two axes cross. And so as x approaches 0, and we do have to look from both sides, we're looking at what's happening on the function. So what is occurring on the function? And we're looking at this and we're saying, well, the function itself is approaching what value? Or is it approaching a single value? And in this case, it is. It is approaching 1. Okay? So we would come in here and we would say this is approaching 1. Okay, so the limit of this function as x approaches 0 is equal to 1. And then we could look at, let's look at another one. Let's look at the limit as x approaches 3 of this function. So as x approaches 3 of this function, so what is happening right there? So as x approaches 3, so here's 3, so as x is approaching 3, so as we're marching the x values in closer and closer to 3, what is happening, getting arbitrarily close to 3, what is happening on the function? And you can think of it as tracing the function with your finger. So what's happening with the function? Well, the function is approaching the value 3. And I'm going to write these actually in red. So the function is approaching 3. So we would say that the limit of the function as x approaches 3 is equal to 3. Okay, let's look at another one. And actually, I'm going to change a little something on this. I'm going to do this. I'm going to say, oh no, look at what I did. I erased the whole thing unintentionally. And this is actually what I want to do. I want to make a little hole. This is having struggles here with my there we go. That was what I wanted to actually do. I'm going to make a hole in the graph. I'm going to punch out a little hole right there so that if we were to actually consider what happens to f of 7 is undefined. the function isn't defined right there. So right there at 7, if we were to try to say what is the output value, the function value there, it's an open hole. It's a hole on the graph. So it is actually undefined at that particular point. So f of 7 is undefined, but we could consider what happens to the limit as x approaches 7 of the function. So the limit of a function and the value of a function at a point are two different mathematical concepts, and we have to keep that in mind. So in this case, as we're looking at this one and we're saying, well, what's happening to the function? We're saying, well, the function itself appears coming up this direction to be approaching 5, and coming this direction, right, as we march the x values closer and closer and closer to 7 on the x-axis, what's happening to the function? How is the function behaving? And the function is behaving in such a way that it is actually approaching 5. The limit of the function is equal to 5, but notice that the value of the function is actually undefined. So what does that mean? Why does that make sense in this concept of a limit, in this intuitive definition of a limit? So if we come back over here, that's this piece that I was mentioning right here. Suppose a function is defined for all x near a, except possibly at a. That's the case where we have a hole right there, or something of that nature, right? The function itself does not have to be defined right at a. When we think about a limit, we're considering what is happening around x equals a, getting arbitrarily close, like infinitely close. X gets infinitely close to a. But what happens right when x equals a is not important to us when we consider a limit. A limit has to do with the behavior around, of the function around the value x equals a. Okay? Okay, and one more piece, because we're going to explore it in this section as well. And since I have this graph and I threw in a vertical asymptote on this graph, I do want to just talk about it. We haven't defined an infinite limit quite yet, but we can talk about intuitively if we talk about what is the limit of f of x as x approaches 5. Okay. And as x approaches 5, notice what's happening here on both sides as we're letting the x's get closer and closer to 5 from both directions of 5 here. Notice what is happening to the actual function. The function is decreasing without bound on both sides. It's actually a vertical asymptote on this particular function that I created. And so what we can say right here is if that behavior occurs where we decrease without bound, we can actually say that the limit of the function as x approaches 5, we can capture that decreasing without bound with negative infinity. If it decreases without bound, meaning it just continues to get larger and larger and larger in such a way that is infinite, decreasing without bound, then we can say that the limit of the function as x approaches 5 is actually equal to negative infinity. So that's a kind of an overview, jumping a little bit into those infinite limits as well, but that gives us a sense of what we're talking about when we talk about a limit, and that limit notation gives us a visual. And so now let's look at a specific example. Let's actually look at a specific function. And there is going to be a couple of ways in which we can actually look at limits. And the first two that I want to look at are graphically and with a table. And so when we consider calculating limits, if we have a function, we can do that by looking at the graph of the function. That's one way to compute a limit. Or we could create a table. That's another way to look at a limit. Or we can get into some more algebraic and more sophisticated techniques. And we'll build up those techniques over the next two sections. But for now, for our first example here, if we come across the function, and it's the function f of x equals negative 1/2 x squared plus 5x minus 2, and we want to find the limit of that function f of x as x approaches 4. So what can we do? Well, I actually put it into Desmos, and I'm going to take us over to Desmos so that we can take a look at both of these two techniques. But what we can do is we can graph it. Obviously, it's a parabola opening downwards because of the negative 1/2 x squared, and we can consider what's happening as we approach 4. We can also do that same thing, but using a table to get an estimate. And so I'm going to go ahead and go over to Desmos and show how I do that in Desmos, but you can use, with this particular function you could have graphed without any technology, but you can use a graphing calculator, you can use Desmos, there's GeoGebra is another one that can be used for graphing, but find something that you can use so that you can visualize these functions. Find a tool that you like to use, a graphing tool that you like to use to visualize these functions. Okay, so here we are in Desmos, and we can see the graph of that parabola, same one I had over in my notebook. We can see the graph of the parabola, and we're considering the limit as x approaches 4. So as x approaches 4, if we take a look right here, so as x approaches 4, 4 would be right here on this parabola. If we were to graph it, we could actually put it in we could put in, let's say f little f of 4. And we can see little f of 4, it's this point right here. We could even, Desmos also has the ability, you can actually just put your cursor right on it. So we can see right here that the function's value at 4 is equal to 10, but that is not actually what we're considering. What we're considering is what the limit is. So remember, this parabola has a value at 4. At x equals 4, this parabola obviously has an output value of 10. We can see it on the graph. That's not so much what we're looking at, though. We're looking at the behavior around it. And so since it has that value, and it's what we call a nice smooth continuous curve, which we can define in a couple of sections, but it's this nice continuous curve, right? There's no holes, there's no asymptotes, nothing like that right here. So we can see that the function itself, as we approach as x approaches 4, the function itself from both sides is going to approach 10. So graphically, we can see that this limit should be 10. We can do it with a table as well. So to do it with a table, we pick x values close to 4 and getting closer and closer. Now we do need to make those values come from both the left and the right side. And so when we're thinking about that, coming from the left side of 4, we got to march in from both directions. So coming from the left side of 4, maybe we start with 3. Notice what I did right here. I just added a table. I added a table here in Desmos and x1, and then I made the output value f of x1. That gives me a quick way to do these calculations using this graphing calculator Desmos. And so what I could do here is I could say 3, and the output would be 8.5, and I could say 3.5, and the output would be 9.375. I could get closer, 3.9. And you can see I'm actually graphing those points as well in this table right on the graph here. I could say 3.9, and now we're at 9.895. I could say 3.99. Let's get really close. Let's keep going. 3.999, right? And we can see right there that we are very, very close to 10, 9.9989. And go as close as you need to on when you're taking a limit and you're computing it with a table. Get as close as you need to see the behavior. And so then we have to go from the other direction as well. So coming from, if we think about 4, coming from the other direction, right, we're coming from the right side of 4 now. So maybe starting at 5, right? We got 10.5, and then maybe we try 4.5, right? Get closer to 4, and then 4.1, right? Continue to get closer and closer to 4, 4.01, and maybe 4.001. Okay, and we can see with each of these, just like coming from the other direction towards 4, coming from the left side of 4, we can see that these values as well are all approaching 10. And we can see that also on the graph. We can see those points getting closer and closer and closer. If we were to zoom in on that graph, we can see, and I mean, it's, it's so tiny, we went so close to 4 on the x-axis, but you can see those points are just approaching as we come in. Those are like the arrows that I drew on our first graphical example. Those are like the arrows that I drew. Those function values are just getting closer and arbitrarily close to this value 10. This 10 is the L in our definition for the limit. And so let's take this back over to our actual notebook here, and let's write out the notation. Okay, back in the notebook, and so let's put this back into the notation. So graphically we could see on the graph that the limit of this function, and I'm going to go ahead and write the function this way, 1/2 x squared plus 2 as x approached 4. We could see that that was actually approaching 10 when we looked at the graph. We could see that that limit was approaching 10, and I can refresh the graph here. We could see that function itself, as the x values got closer and closer to 4 on the graph, we could see that the function itself was approaching 10. We could also see that using the table. And so remember on the table when we created the values for the table, and if you are picking your own values to create a table, remember because we were focused in on x approaching 4, that we had to pick some values around 4. So, we had our value 4. If you want to think of it like this, you could think of it as a middle line in the graph, and then you need to pick values that are approaching 4. So, we did 3, and then 3.5, and then 3.9, and then 3.99. And when we talk about it, I don't have the f of x values. We looked at those over in Desmos, but you can plug those into the function and figure out what those estimates are. But we have to approach 4 from both the left and from the right. And so on the other side of it, right, coming up the other direction in this table, if you wanted to write it this way, we had to go 5 and 4.5 and 4.9, not 9, that's going to 5, 4.5, and then 4.1 and 4.01 and so forth, right? Getting as close as we can to this point here, 4, that we're trying to consider what's happening. And then we looked over here at what was going on with these f of x values, and they were approaching the actual function value, because in this case the function did have a value at 4. It had the same value as the limit. Okay? So f of 4 was actually in fact equal to 10. But we found also from the table that the limit the limit of the function, negative 1/2 x squared plus 5x minus 2 as x approached 4 was in fact equal to 10 as well. So we got the same answer whether we looked at it graphically or with a table. And honestly, the table is just the mathematical calculations for the visual we're getting out of the graph, right? The graph is the plotted points from the table. Okay, so that's how we can look at a nice little function like a parabola. But let's look at a different type of example. What if we looked at a rational function? So what if we wanted to look at a rational function? So let's consider this rational function. So if we have f of x equals x squared minus 4x over x squared minus 16, and we wanted to actually find the limit of that function, x squared minus 4x over x squared minus 16, as x is approaching 4. And I want you to take a look at this. Like 4 is going to be a bit of an issue, right? Because if we were to plug in 4, is going to give me division by 0, right? 4 is definitely going to give me division by 0, which is a problem, right? So I'm kind of thinking my little like thought bubble here. Like when I think about what that limit is, I'm kind of thinking like, well, x equals 4 would create division by 0. I mean, who cares? There's something up here. I'll just put a little number right there. But it definitely creates that division by 0. And at this point, right, we've got division by 0. At this point in our mathematical careers, we know division by 0 is a problem, right? We can't have division by 0, or division by 0 gives us like interesting points on a graph, shall we say. Okay. Now, again, remember that we're not necessarily concerned when we talk about a limit. We're not necessarily concerned about what happens right at that point. So this division by 0, actually, while it might create some sort of interesting behavior on the graph itself, right at 4 is not what we're concerned about. We are concerned about the behavior around 4. So remember, when we talk limits, this is asking us to consider the behavior around 4. So this is the behavior. We're looking at what is the behavior of the function f of x around x equals 4. So that's what we need to consider. So if we were to actually graph this, and so let's consider again our two different ways to do this. If we were to actually graph this, and let's refresh that, and it's going to come up. If we were to graph this, we're going to see that we have a rational function. It's going to have both a vertical asymptote and a hole on this graph. Okay? So I'm going to go ahead, and I just popped it into Desmos, and we actually have this right here. Now, I want to show you that if I were to drag this along here, and I were to try to go right to 4, and I'll see if I can actually, right there, and you, oh no, it's actually off the screen, so let me scroll it over here so you guys can see. So here is this function graphed in Desmos. So I graphed this function in Desmos, just typed it in, f of x equals the function we're looking at. And if I were to drag this along and kind of look at the points on this graph, you can see that point that we're considering right there. It says 4 is actually undefined, and my cursor is kind of over it, but there's actually a hole in the graph right there. And that is because of that division by 0. That division by 0 at 4 right there gives us, if I can, I'm trying to toggle it so it gets right there. It gives us an undefined, the function itself is undefined right at 4. Okay? And so when we look at this graphically, we have some kind of interesting behavior that I'm going to kind of just zoom in on here, so get a little bit of a graph here, and we definitely have this hole. So if we think about at 4, we have a hole on the graph. There's actually a hole on the graph right at 4. So what we need to consider is what is happening around it. Okay, so at x equals 4, f of 4 is undefined, which means there's a hole. There's a hole. It doesn't really look like a hole, right? When you actually look at this Desmos graph right here, if you use a graphing calculator, you have to always be smarter than your calculator. So if you're using a graphing calculator and you see a graph that comes up like this and you don't see the hole, right? I only saw that hole. I was only able to visualize that hole for you guys by actually pulling my cursor over the Desmos graph so that you could see it. It doesn't just automatically like show up on this Desmos graph. So you have to make sure that you're careful of little things like that. But there is definitely a hole in the graph. There is a hole in the graph here. And so we want to be careful of that. But what we're looking at is not necessarily what happens right at x equals 4, right? We know already. That's what I've said. We've just talked about that at great length, right? F of 4 is actually undefined. The function isn't defined there, but that is not what we're looking at when we look at a limit. We're looking about what happens around that point, right? What is the function's behavior as the x's get close to 4, not right at 4? And so if I could zoom in here a little bit, and we'll do it with a table too so we can see the exact values. If I could zoom in here a little bit, right, we can start to see that getting close to 4, that the function is, oh no, and I'm zooming all around, that the function is approaching a single value here. So what would that value be? Well, coming from the left and from the right, it's appearing to go, and I'm kind of just toggling again on this. I'll scroll over a little bit. I've zoomed in here, and we can start to see that it seems to be approaching graphically. I see as I'm getting closer and closer, I'm looking at that y value 0.497, and on the other side 0.504, 0.503. This is approaching 0.5 or 1/2. And so graphically, as I'm looking at that, I can see that this point right here on my graph, using that graphing calculator, is 1/2 or 0.5 if we like decimals better. So what I can say here is that the limit of x squared minus 4x over x squared minus 16 as x is approaching 4 is equal to 1/2. And I can do that same thing using a table. So if I'm going to use a table, again, I have to make sure that when I create my table that I look at it from both directions. And so we can definitely use a calculator to do the computation, but when we're setting up the table, we want to make sure that we're plugging in values from both sides of that number, x equals 4. And so if I've got x equals 4 right here, kind of working my way, this is how I like to set up the tables. I put the value right in the center of the table, and then I work my way towards it from the left and from the right, top and the bottom, basically. We do know this. The function itself is undefined at 4. I can fill that in. This function is undefined at 4, but what's happening around it, right? And so maybe we start at 3.5 and then 3.9 and 3.99. And coming up the other direction, maybe we start at 4.5. Sorry, it's getting small and towards the bottom of my table there. And then maybe we do 4.1 and 4.01. And I'm going to go to Desmos to do those calculations simply because it's a little bit easier and you're going to use a calculator as well. And so if I go over to Desmos to do those calculations, I can do that in Desmos right here. If I were to add, if you want to use Desmos like I am, I just add a table right here, and then it gives me an x1 value. And then right here where it says y1, instead of having it plot x and y points right here, I'm going to actually have it generate the x and y points from that function. So I can type f of x1. So I want it to actually use the x values that I'm going to type in here to give me the f of x values. And then I type in the x values that we have there. So I can type in 3.5, I can type in 3.9, 3.99. Notice what happens when I type in 4. Desmos, like I said, Desmos does know that the function is undefined at 4. It just doesn't really look like it graphically unless we were to zoom in or put our cursor right at 4. So don't let the graphing calculators trick you on these, okay? A function where we have division by 0 is going to have some interesting behavior, either a whole or vertical asymptote, something like that, okay? And so you can see right here from the table that the table, obviously the points are definitely approaching 1/2. And then coming on the other side, I'll type in the same points, 4.01, 4.1, and 4.5. And we can see clearly that this table coming from both directions is going to give us a limit of this function, x squared minus 4x over x squared minus 16 as x approaches 4. It is definitely giving us a value of 1/2. Okay, and so there is our two different ways that we can do this. Okay, I want to mention just one more way, and this is jumping a little bit ahead, a little bit of a preview to some other techniques that we're going to talk about rather than just graphical and table. But I want to talk about something, and some of you might have noticed that both the numerator and denominator of this function factored, and so there is actually an algebraic approach that we could take to here, and I'm going to go ahead and just show that to you here just to end this video, because this algebraic approach is pretty nice, and we're going to spend more time with an algebraic approach in the next section, but I think at this point it's also nice to consider. So if we think of that function, f of x again, x squared, and then of course this comes over x plus 4. Now, what that means is that this function is actually equal to x over x plus 4 when x is not equal to 4. Okay, we do this piece has to be specified here because the function that I've looked at right here actually is defined at x equals 4, whereas the function that we started with is not. So we do have to be careful. There's some domain issues, and I'm kind of waving my hands a little bit, even though you guys can't see me, I'm waving my hands. There's a little bit of hand waving here, and when we get into the algebraic techniques, we will get a little more specific. But intuitively, these two functions are equivalent except at that one point. But remember, that one point that we're concerned about is not necessarily important to us when we're looking at a limit. It's what happens around it. And so these two functions are exactly the same, exactly equal, except at x equals 4. So when we consider the limit, and we take the limit of x squared minus 4x over x squared minus 16 as we're approaching 4, that's actually going to be the same as looking at the limit as x approaches 4 of x over x plus 4. And if we think about what happens right here, as x approaches 4, the numerator is going to approach 4, and the denominator is going to approach 8, and this is going to be 1/2. Even though, okay, and I don't want to gloss over this. I want to make this point is really important. Even though the actual function at 4 is undefined, the limit is 1/2. Okay, and we've actually shown that in 3 different ways, right? We showed it graphically, we showed it with a table, and now we've showed it with this more intuitive algebraic approach. Okay, and so there are 3 ways to consider this. I'll try to get them all on the screen. My screen keeps freezing up on me today, but there we go. Okay, and you can see those 3 different approaches, but we're still getting that limit of 1/2. However we come at it, we still get that limit of 1/2.